Welcome, if you're watching this video online, to the first class with Matt Miller, doing the reverse engineering portion. We're going to do a little more about debugging and running through binaries. I am Brian Brake from the Breaking Down Security podcast, and we are doing these trainings. This is the first of 4 sessions where we're going to run through various methods on how to walk through binaries and deal with some ARM architectures as well. So there'll be additional information at the end of class on how to listen to the podcast if you want, or to contact Professor Miller if you have questions independent of the video. So I'm going to cede the rest of my speaking time to Mr. Professor Miller.
All right, had to get everything set up there. Thanks, Brian. So this class will be a little bit different than our previous one. So we're going to do a little bit more hands-on in this class. So we're going to sort of start from the basics, and we'll go through and just talk about some of the high-level topics to start off with, and then we're going to go through and actually look at code and look at the correlation between a high-level language, so for example C or C++, and then what ends up getting generated on the back end in the assembly. So earlier, if you looked or watched the assembly lectures, right, you'll get a introduction into assembly, and that's kind of where we end up sort of starting with reverse engineering for this class. Now, you can reverse engineer other languages that are a little bit more readable, and they're not going to be assembly. So you could disassemble ActionScript or Python. All the code is there generally. So there are other things that you can do, but we're not going to necessarily talk about those. So we're more specific on the malware side of things here. So to start, we often talk about, and we'll use the word disassembler as something that we use. And so the input to a disassembler is some binary data or some program. So if you have a program, right, that's going to be your input. If you have maybe some shell code that you want to examine that is getting run, right, that would just be a blob of binary data, and we would go ahead and you could disassemble that as well. And then one of the keys is that a disassembler has to be able to read different binary formats. So there are going to be several different ones that we'll talk about in class. There's probably 2 main ones that we might see, or 3, as far as if you're looking at normal apps when we're going to go ahead and disassemble. And then the output, so the disassembler is going to read that binary data. It's going to try and interpret what the assembly instructions are for that. So it's going to generate some sort of assembly representation of that. It will try and do things like determine where function boundaries are. So where is the beginning of function, where is an end of a function. Add references where, you know, certain code calls other code. It will try and put those in. But this is a very error-prone process, especially when you have people who are trying to thwart your activities, right? So they will put in their anti-disassembly techniques, and so that will make it so it's even more difficult for you to figure out what you're looking at. And then we have the notion of having a database. And so a database is, once you've loaded that binary data in, it saves that information into a database so it doesn't have to go through and parse it again. And it can be a lot faster than just trying to reparse the binary every single time. And there are 2 types of disassembly. So sort of, you know, in the beginning, right, we had this thing called dead listing. So dead listing is you basically start at the very first set of bytes, you start disassembling your way down, and when you get to the end, you get to the end, and hopefully you found all of your functions. Now, this can be good, can be bad. So you might end up not categorizing things right. So if you know that somebody's doing a dead listing, you could throw in some instructions to make it think that there's a function where there's not a function. And so that can be a problem. So we also have the notion of recursive descent. So basically within our binary programs, we have a starting address that says, okay, when you start executing this program, here is where you're going to go ahead and start. And so recursive descent basically has a list of all of the different addresses that it has disassembled. And it starts at the beginning one. And then every time you have a branch, so if you have a jump, you have a call, you have a return, all of those are going to basically create new branches, right? So a call, right, you're going to jump to that other location, but then when it's done, right, you're supposed to come back and execute the next instruction. So recursive descent will put both of those addresses onto what we call like a stack or a list or a queue and say, okay, these are things that I need to do. And then it pulls one off the top, right, and starts disassembling that. And so it's a way of starting at the beginning and only finding things that you think are going to be known. But again, we have actors who are out there trying to break our disassemblers so that we can't figure out what they're doing. And so they will, again, put in tricks to trick the recursive descent disassembler into doing something that maybe it didn't want to do or it wasn't very good at doing, or it's broken. All right, so I am going to show a little bit of IDA in this class. Part of the reason is that, so Binary Ninja, which is going to be the other one that we're going to look at writing some Python for. One of the drawbacks to Binary Ninja right now is its support for Windows binaries. So it does, right now, it does a really poor job on a Windows binary where you don't have this extra, what we call PDB, which is the listing of what symbols and what names for regular functions are. And so Binary Ninja doesn't have all that because they are sort of more in the Linux community. They are a lot better at loading all that information for Linux binaries. Whereas IDA sort of started out with its roots in the Windows community. And so they have a lot better support for Windows binaries and a little less support for the Windows ones. Now, why would you want to choose one over the other? I don't remember off the top of my head what the going rate for IDA is, but it's, I don't know, $1,500–$1,800 for that. Whereas if we look at Binary Ninja, it's a lot cheaper. So it's in the $200 or $300 range, depending on what license you get for it. So, and also IDA, they have a very, we'll say, pedantic licensing scheme where you buy like one license for one computer and that's $1,500. You want a different OS, right? That's another $1,500. I mean, they charge you up the nose for their licenses, and they do really well at disassembling. So we have that. So I'm going to go ahead and let me see if I'll just pull up a simple example here. So this is the, and my support has expired. Great. All right, so when IDA starts loading, it says that I already have a database, right? So I talked about how we have databases that are going to be associated with it. So I'm going to go ahead and overwrite. So we're going to start from the very beginning. And of course, it wants to open on a different screen. All right, so the first thing that IDA does is it checks to see, so I'm loading an EXE. We're going to talk about portable PEs in a second. But it sees that this is Windows and it's using a portable executable. And so it's basically got a lot of different settings. I typically pick the Meta PC, so disassemble all opcodes. Right? So it's going to try and figure out all the possible opcodes that we can have, but we could pick, and of course now it's going to go crazy here. Let's try this again. Oh, okay. Let me try it one more time. Nothing like a live demo. Okay, I will not pick that other one. All right, so I usually use MetaPC and then rename DLL entries, right? So IDA is aware of what the DLLs are, right? And so and that's a whole process, and we can talk about that. And then create an import segment. That's also fine, right? So the defaults are usually are fine for a typical binary. So once IDA starts, it's going to go ahead and I don't know if you guys saw, but on the very top, right, it sort of analyzed this binary as it went, and it's got different colors for the different sections of code that it has figured out what they are, and it's doing analysis on it. And you can see that it put in, right, all of these different names, right? So I have one function in here called main, and we've got some assembly code, and we're going to look at this assembly code and what the origin of it was. But if we notice here, right, inside of this, we have all of these names of functions, and that's because IDA knows what the signature for all these different functions are, and so then it can basically apply a name to it. So when I go and look at a binary when it's in IDA, I can tell that, okay, here's a function called puts. It's called _put_s. And I don't need to go through and read the assembly. I can read the documentation on puts, because puts is a standard library that's going to come with Windows and Linux and the different standard libraries that we have. So all of these, I know that they probably do the typical thing, and so I don't have to try and reverse engineer them. One of the things you don't want to do is go down the path of trying to reverse engineer code that you could just as easily have read the documentation of, okay, here's what printf is, instead of, you know, going through puts and saying, okay, what is all of this stuff that it is doing? So that's one of the things that you'll learn, is to try not to reverse engineer code that you don't need to. And then, so as my slide talks about, so there's a couple different views in IDA, and from what I hear in the grapevine, these features are maybe coming to Binary Ninja. So some of these, Binary Ninja basically has two views, which is like their assembly view and then their hex view. So if we're in the disassembly view, we'll see that it says push EBP. And if we click on the hex view, it'll actually show us the binary opcode for that, right? So it read the binary value of 55, and then it interpreted that as, well, 55 is the opcode for push EBP, right? So when we talked about assembly, we've talked about what instruction is this? Well, this takes the EBP register and it pushes onto the top of the stack. Or if I say move EBP ESP, right, that's copying ESP into EBP. Well, if I go into the hex view, I can see that that is 8BEC. That is the binary data for that. And this is all, again, it says hex view, which means this is all stored in hexadecimal form, right? So we got values from 0 to 9 and A through F. We also have a structures tab. So we'll talk about structures in class and how those are defined, but basically a structure is a way to take a bunch of data that is related in some sense and putting it together in one, I'll call it object, one structure, so that we can manipulate it in one way instead of manipulating those pieces of information separately. So the easiest way to think about it is, if you have something like an employee, right, they're going to have an ID, first name, and a last name. And we can, instead of having 3 arrays to store all of that, we can have one structure that holds all 3 pieces of information in one. I'll skip enums. Imports. So for any library to do anything that's useful, anything at all that's useful, it has to basically use other libraries that are built in. So Windows has the kernel32.dll. I think this is all this one is using. But these are functions that are provided by the operating system that the user program can use in order to do things. And they're typically easily named, right? So we got something like write file, right? And if you don't know what that is, right, you can look up the documentation on MSDN to see what does write file do. But because all of this is stored in what we call a DLL, or a dynamically linked library, basically the operating system has one copy of it, and then every program that wants to use it is linked to it dynamically. So it points to it on the fly. Well, that's where we get the dynamically linked library, or DLL. And so all of these imports represent, these are functions that our process is going to use. And typically, right, if you have a normal program, it will have a bunch of things that it imports. But one thing that you will maybe run across is these things called packers. So what a packer does is it takes a bunch of assembly code that the attacker wants to run, it packages it all into some data, and then it goes ahead and actually resolves all of the imports dynamically on the fly. And so when you go into the imports, you'll see maybe 2 or 3 different imports instead of, I don't know how many there are here. Looks like, 64, right? I got 64 for just a standard binary. And so looking in the imports can tell you if something is packed or what functions does this use, right? If it's not packed, I'll see all of those functions. And so you might end up seeing in here that it's using networking functions. So then you know that that program is going to make a network call, and then you can go ahead and look at that. And then exports, typically a normal binary is only going to export or expose the start function. If this is a DLL, all of the things that some other program could link against would all be in the exports listing. And then IDA has a lot of buttons. So let's see if we can, I'll open one more here just to look at. So the strings. So probably your easiest place to get beginning clues on a simple binary would be to look in the strings function. So the strings function is going to have information about sequences of characters. It's usually 3 or 4 or more ASCII characters followed by a 0 within them, and 0 is the null terminator. So a majority of these are just standard ones that you get when you build a Windows application out of the box. But then we come down here and we can see that I have a string called hello world, a good value, a bad value. It looks like local equals %d, global %d, right? So these are strings inside of this binary that might be unique to it and they might not. And then things that you'll learn as you're going through. So I tend to, and a lot of people tend to like the sort of listing view where you can just basically see everything going linearly from top to bottom. You'll see things like a jump, and then it'll put a little arrow to say, okay, this is where it jumps. And if you're in IDA, and this also works in Binary Ninja because they sort of cloned a lot of the keyboard shortcuts, if you hit space, it will go from the linear view to the graph view. And so the graph view is going to basically show in a graphical manner, red meaning not the false choice, green meaning the true choice. We can see that we go from one block to another to another. And so this allows you to visualize sort of the flow, right? So if I look at this one, I see that I'm starting at the top, I make a decision here, and then I keep going straight forward. Now, if I had an arrow back, then I'd see that there might be a loop indicating that something might be done over and over again. All right, so that's kind of a little basic intro to IDA and why we do want to use IDA sometimes. If you have the ability to use it. It is, again, it is very expensive. I think there is a free version that doesn't offer saving, and so it's quite old, but it still gives you a lot of the basics. And then if you really need, IDA, and a lot of people do, then, you can have your employer pay for that. All right, so we're gonna just look at the basic program that I had here that originated this assembly program, and we're gonna see a little bit of a correspondence between the two. So for example, we see here that I have a local variable and I set it equal to 17. So if I come in here So first of all, right, if you see a hard-coded value within IDA or within Binary Ninja, if you right-click on it, it actually will in IDA, it'll give you options to look at this in different bases, right? So this is 11 hex, which happens to be 17 in decimal. So I can see that what the compiler did is it decided that it was going to use, and it says EBP plus var4. Well, what is var4? Well, it's actually EBP minus 4. But if we look in here, we can see that if I highlight var4, right, so that's all EBP minus 4. And again, all of our EBP with a negative value are local variables, right? So this is a local variable. Here I'm moving the value of 17 into the local variable, and I can rename it. And again, keyboard shortcuts should be the same. So if I type N, I can rename it, and I'll just call this local. Now, the benefit of that, right, is that I renamed it in one place, and then it renamed it in every place. And so when you start using a disassembler, you'll want to add things that give you information about what you have figured out when you're trying to put this puzzle together. Because if I had given you this program before, you would have to figure out, okay, what does compare dword to 48, right? So it's got this value here. Compare that to 48. Okay, well, what is that? Well, we can see here that there is here's a call to printf. Here's a call to scanf, right? The first argument to scanf is %d, and that's the format for scanf. And we can see that in here, right? We can like put that correspondence together. So my first argument is the last thing that got pushed onto the stack. My second argument is this address of global, right? So we actually have a global variable, which is at dword d blah, 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 blah. So I can change that. I type N for name, and I'll just type global. So now I can see that there was a call to scanf. Global got its value from scanf. Here we're comparing global to 0. And then if it's less than or equal to 0, oh, come on. Right? So if it is less than or equal to 0, it's going to take the green path, which is going to say bad choice. Right? So here, if global is greater than 0, right? So my first if got sort of inverted, right? It's saying less than equal, go here, right? And then it's doing another compare. And again, I can convert 48 in hex to decimal, and I see that I have compare global to 72. Okay, that's my second part of my if, right? And so one of the benefits of our high-level language is that it automatically takes care of the fact that, okay, in assembly, I had to break down this into 2 different compares so that I could figure out if I need to do good value or not, right? And so we can see that the compiler took care of a lot of that already for us. And then we see here, we see a call to printf with here IDA, again, has looked at the offset that was pushed in here, and it actually just has an actual hex value 40D018H, but it saw that the thing at that location looks like a string, and if I double click on it, I can see that it is an array of characters, and I can go into my hex view and see the actual hex values. So there's the GOOD, 20 is a space, VALUE, and then we have a null. Right, so it automatically figured that out. And again, we'll look at doing some of this in Binary Ninja, but we'll see similar types of things. Oh, okay. And then, well, let's go. And another thing, if you hit escape, it is like going back, right? So I had control clicked onto good value to go into that, double click to go into that. If I hit escape, I can go back to where I was. So both of these blocks come into here, right, using a jump, right, to a particular location, or this one actually just falls through in that it executes this one and then it just keeps continuing on. So if I push space, we can see that one of them has a jump, right? The other one just falls through. So that's, again, what the compiler takes care of for us automatically. Let me see if there's questions. So with DLL hijacking, is the DLL placed in a certain location and called, or is it included in the code and decompiled? So there are a couple different ways that DLL hijacking can occur. So one of them is that the way that a DLL is loaded is that a DLL, if you're looking for a particular DLL, the way the OS looks for it is the first place it will look is in the current directory where the executable is being loaded. If it doesn't find it there, then it has a set of paths that it's going to go and look for. And so one way to do DLL hijacking is to basically put a DLL in the same directory as the binary, and then the OS would, by default, just load that. So that's one way. Another one is to basically, on the fly, basically go through and hook all of the calls to the function so that they go to your DLL instead of the original DLL. So it would go to your DLL first. You could do some processing, exfiltrate some information, and then have it go on to the new DLL. So typically it's not included in the code. It's just you're taking over that call to a DLL function. Good question. All right, and then so I find this site actually very useful for a lot of students. So there's a guy that, I don't know what his name is, but he's got this website called gcc.godbolt.org. And so what this does, so I have that program that I just got done describing to you. And so basically, and this only works for GCC, so it is limited in that sense a little bit. And if you're wanting to do this, because we've talked about 32-bit, you want to put the -M32 inside of this as a flag. So that's a flag saying, compile this 32-bit instead of 64-bit. And so basically, as you're putting in a program, if you highlight a particular line, so let's say the beginning of the main, and it might be a little bit hard to see, but when I clicked on this, it actually highlighted this set of code up here, right? So the beginning of the function, right, we can see that it does, again, it will do some sort of weird things with this. Here, let me put -0. Let's see if that changes. Yeah, a little bit easier. Right, so some of these are things that GCC is doing, right, that don't really matter a lot to normal people. But we've got some, right, this is aligning of an address. This is saving an ECX, a value. I think there's probably a cookie in there. But we can see some of our typical things like we've talked about: push EBP, move EBP, ESP, right? It's saving the value of ECX. And then we're doing a sub ESP20, right? So we have some local variables that we're going to be using and actually some other parameters. And so it's actually doing this by default. And so we can go through this and we can look at every single line that we have. So this one is the purple. Oh, come on. That purple. So here we're doing printf on hello world. And so we can see that, again, we're subtracting 12 from ESP. Now this right here, if you're coming to this for the first time, you're saying, golly, what is the compiler doing? It's being all crazy. So one of the things that they've implemented in newer versions of GCC is they align the stack to a 16-byte boundary. And so up here, it did this AND with ESP on -16, which basically the last, I believe, 2 or 4 bytes, or 2 or 4 bits of the address end up getting set to zeros, so that it's on an even byte boundary. And so it knows that this is on an even byte boundary, and it knows it's going to push 1 argument. And so to make it another even byte boundary, it subtracts 12. And then it pushes something. So now we have 16 subtracted, and then it goes ahead and does add 16 to get back to, right, we subtracted 16, so we got to add 16. So you're going to see that in here where it's doing additional subtracts, so that way it can always keep that byte boundary even. And that's because there are OSs that are now making it, that's harder for shellcode to sort of get started. So at every step, we can actually highlight or even reverse highlight. So I can highlight a block and it says, okay, this is doing that if, right? Move EAX, the value of global, do a test. If it's less than or equal to jump to L2, and it shows me where L2 is. Again, move EAX global. So it loads it again, even though it just got done loading it, right? Does it compare with 71, jump greater than to L2 again, right? So it's implementing all of this logic. But the nice thing about this is that on the fly, it can go ahead and show you that correspondence between high level code and low level code. And being able to see that is one of the things that's going to make your reverse engineering job a lot easier, is understanding that relationship. All right, so executable formats. So basically every single operating system has their own, what we would call native file format. So this is a binary format that the OS has the ability to load and start executing. So any EXE or DLL on Windows uses the portable executable format. So portable executable is a way for, again, we talk about dynamic linking, right? So that's one thing that PEs provide, and they're kind of an extension of the old DOS programs, right? So it's a maturing of the DOS format, so that way we could have more extensible code that we could run. And so Microsoft uses that for their executables. The Linux, of course, being all open source, right? They have the ELF format, or the extendable and linkable file format. And so that's their native one. And again, because they are Linux, right, all the documentation on this was originally published right when they started building it. Whereas Microsoft kind of said, well, why would anybody want to look at the portable executable format, right? It's just the file format, and nobody should be looking at the binaries. So people have had to, many years ago, had to start reverse engineering it. Now Microsoft sort of more supports that in their usage. And then we have on the Mac, they have the Mach-O, and this is because the Mac on OS 10, right, they used the Mach kernel, which was originally sort of based on BSD, which is what the Mac is. And so this Mach-O kernel, that's the executable format for Macintosh computers and Apple devices. So here's a diagram that you can find online, and let me make my show thing a little bit bigger here. It kind of barfs on really big images. So one of the things with file formats is they basically define, okay, here is exactly how many bytes are going to be in this section. Here's how many bytes are going to be in this section. And then we have other sections that could be longer or shorter than others. And so again, right, this talks about, okay, there's a header, and with a header, it has some technical details about the executable and what the executable holds. And that header is composed of, and again, right, so this is using an old format in the beginning, right? So we had this thing called a DOS header, and it says, hey, this is a binary, right? And then the PE header says, hey, this is a new binary, right, or a modern one, right? And the PE header defines that we're going to have these optional headers and data directories that basically say, okay, here are all the different parts of this executable. You know, we're going to have things like code, but we're also going to have things like imports. We're going to have data that is going to be built into the binary. You can actually have resources that are built into the binary. So all of this stuff has to be included in the binary format. And so, right, one of the things, if you've ever looked at any binaries, and I know this is probably the super tiniest text that you'll ever see, but if you go ahead and look up this PE 101, you can find this image, and I'll put it on the drive for everybody so you can look at it. But actually, the first two characters in every binary that is a PE are MZ, and I believe it stands for Mark Zippelwig or something like that. So he was the creator of the PE or the DOS file format. And so, if you're going to just like, put an Easter egg in, you might as well put your initials in the beginning of every single binary that's ever been made. So every single Windows binary starts with MZ. And you'll actually see scanners that look at data going across the wire, and they look to see, does it start with MZ? Well, then maybe it's a PE file, right? Or at least a PE file format. So this is the DOS header, and if you guys ever, I have one open here. Let's look at the beginning of this file. Let's go to the hex view. Actually, this is not going to show it. Well, let's do this. I can pull it up. So a program that I often use just to get a real quick, and that's on Linux, a real quick view of the hex values that are inside of a binary. It can convert both ways, is XXD. It's sort of a hex editor. I could run the whole thing, but I'll pipe this into head. So I'll just grab the first 30 lines of it. So one of the funny things is that, so with PE files, right, they actually include by default the text, this program cannot be run in DOS mode. Right, that's because when you started off, you had all these DOS programs, and so people would run them in DOS, and that was fine. And then there was Windows, and Windows 3.1, and Windows had the ability to run DOS programs, but then it also had like these new programs that were using the PE format, and so you would try and run it in DOS, and so then it would just basically print off a message saying this program cannot be run in DOS mode. So all of the default compiles of binaries that come from Microsoft Windows Visual Studio will have the text in them, this program cannot be run in DOS mode. And then we'll see later down here, right, we actually have PE, which is, and again, so the MZ, I said it was in every one. It's actually, a, drew a blank on it. It's an indicator of what type of file this is. So it's a magic number. That's what I was looking for. So MZ is a magic number in the first byte. And then we also have a magic number, which is PE. So if we see that it's a PE file, it'll actually have the letters PE at the very beginning, and it's actually PE00. And so when you're going through and verifying that a binary is a Windows binary, you'll see that they'll have MZ at the beginning, and then I can't remember the exact offset, but you'll see the offset of PE within there, and that says, okay, this is a valid PE file if it has that signature and or magic numbers. And then we have a bunch of different headers, and I will actually have an assignment for you guys to go ahead and figure out and actually parse PE files. It probably won't be this time because we still have some more stuff to do, and so we'll kind of talk about how we can go ahead and parse this, and actually there's some built-in stuff that will help you guys out so that you guys can do an assignment that we're going to have. So the PE header says, okay, here are all and it includes this, we have an optional header, and so that includes information about what type of binary it can be run on, information about how big the headers are, how many headers we have, stuff like that. Then the data directories, there are 16 entries in the data directories, and these point to, okay, here are all the different sections that make up a Windows binary, and you have 16 possible ones, but a lot of times you'll have one for the imports, one for the exports, one for resources, one for code, one for the the data section. So all of those are going to get included in one of the 16 data directories. And each one of the data directories then point to a table of here are all the different sections that are located within this binary. So some of them will have all the sections, most of them will have some, but not all of the sections that are listed in there. And so I think this is a really good diagram for like just kind of getting a very high level grasp of what actually exists in the PE file format. And then we also have the ELF executable and linkable format. Right? And again, it has magic numbers. So the very first number is 7F within the ELF binary. And then you actually have the letters ELF, right? And then we have, again, it's going to be similar in that we have a header that tells us information about the binary. So when the OS is loading it, it can say, oh, this is a 64-bit binary and I'm only a 32-bit OS, so it won't work. Or this is compiled for ARM and this is x86, right? And that won't work. Or how big are each of these sections, right? And so we have these, again, we're going to have headers. They're going to tell us, okay, here are all the different sections within the file, and we can go ahead and look at those and be able to examine them from in there. All right, so when IDA loads its files, right, it goes ahead and it actually looks at those magic numbers to decide, okay, which loader am I going to use? So if it sees MZ in the beginning, then it knows, okay, maybe this is a PE file, right? And then it checks and finds the PE00, right? And that magic number tells me, oh yes, use the Windows loader that's going to go ahead and load this. And it actually does, like it says here, right? It does a pretty good job of figuring out what type of binary you're looking with, but sometimes, right, it doesn't. Like for example, when I've done testimony, I've had to load binary data that is not in a particular file format. It's just binary data. And so IDA just throws up its hands and says, this is not a PE or anything that I know about. You're just going to have to do this manually. And so there are times where you end up having to do that. Or if you have firmware for a device where it's using a file format that IDA doesn't support, then you have to do that on your own. All right. And we already opened up our example in IDA. And I'm just going to show you guys opening that exact same binary, the Windows binary, using Binary Ninja, if I can. So again, I think this is currently where they have some work to do, right? So first of all, it located the call stub to start and doesn't actually show me where the program, because they don't know any of the details. It also, every one of my functions here, we can see I have one function that's named start, and that's because it was in the exports. But otherwise, all the rest of my functions are not labeled, right? And we compare that to that. And that's because, again, we don't have a PDB, which is the like programmable database or something like that, program database that has all the symbols. And symbols are things that we have names for, right? So that's, if you ever heard the word symbol when talking about disassembly, it means, okay, I have a name for stuff. And so that way, you, again, right, we don't want to disassemble stuff that we don't know about. So I think, right, it typically, right at the beginning of the binary, we can see our actual main code. And when you compare, yeah, so we have the graph view, right? If I am in it, I can hit space and go to the normal view, and they'll have a little different syntax in the way that they show different variables. So we can see here that, let's see if we can find, there's hello world. right? So their notation here is EBP minus 04, which is var 81. And we can see that in there, or we can see our global. And again, we can rename stuff, type N. And now it puts all of that information. Another thing that you'll also want to do is have the ability to add comments. And again, I believe it's the same in both of them. If you type, let me find this one. So I think that's printf. Here, let's just rename it because it doesn't know what it is. And if you're on a line, you can hit the semicolon, which is to add a comment. And so the number one thing that you'll want to do is you want to write comments in the code. So as you're going through and understanding stuff, you can say, okay, I understand that this is printing a string, right? And then it'll put in here a comment so you can say, okay, I see that this is printf and it's printing the string hello. And then, right, here's another function. Well, I don't know what this is, so I'm gonna have to go figure out what that is. I think that's scanf. So as you're going through your code, you'll want to put in comments for that. And I believe those all work with the free version of Binary Ninja for, I think, x86, and there's another format that I believe that they support. And then one thing, so if you don't want to use Godbolt, that website that we were talking about, you can turn on a lot of the different options that you would see in that. So here is a bunch of different ones that you can, options that you can add in there. So that way you can go through and have a little bit more readable source code as opposed to maybe a dead listing. And that's something that you can definitely do if you want. But the typical way that I do it, right, is I write some code and then I run object dump on it. And so object dump will allow us to, if you're on Linux or OS 10, it will go ahead and tell us information about the, we call it object file, or the file that we are looking at. So we can either look at shared libraries, which are, or partial files, which are like the .o files. And then we can look at .out files, which are going to be the executable ELF files. And so basically, and in this class, and what we've been talking about mainly, right, are going to use Intel syntax instead of AT&T, which I find AT&T irritating and infuriating because there's too many percent signs. So I typically use Intel syntax because that's what I know. The little d is to disassemble and then the file that you're wanting to do. And if you ever have a question on it, you can always do man on it, and it will tell you information about it. So let's see. Looks like I have an OS 10 binary here. Oh, sometimes. Did my things all get messed up? If you don't know how it works or it's different, you can do man. Well, that's just all broken. Okay, let's try this again. All right. And we talked about this in the assembly class, so you can see some of it. And typically the way I do it is I look for the .main. And let me try this again. Followed by that. So grep is a program that will go ahead and search for a string or a regular expression inside of a stream. So this is taking the output of the object dump, right? And I'm taking that output and I'm sending that as input to the grep command. And then I'm looking for the expression .main with a bracket, and that's the actual definition of where main is. And then minus A20 says, give me context of 20 lines after that. And so we'll see this is actually the main in this example, right? So this is one example. One thing that it does do, right, it's going to actually show you the hex bytes that are associated with that, which will come in handy when we get to, so I have a project for the class that might be fun. And so it's going to involve actually encrypting a string and then decrypting it. This string is actually going to be a function, and then on the fly, we're going to decrypt it with a password and print it off. So we'll see how many of you want to endeavor on that project, but it might take you a little while, and we got to build up a lot of things in order to get to it. But it's kind of something that malware can do, right? It can encrypt its data and then use a decryption key to be able to decrypt that data, either via getting some command and control commands that would allow it to decrypt it, or it could try and brute force its own key, right, to make it so that typical scanners may not find it, right? So those are some examples of that. So object dump, again, on Linux is going to be very useful, and a Binary Ninja does a lot better with the ELF type of formats with loading all those symbols. So Jerry asked, do those symbols come from DLLs? So when we are in the imports section, so yes, all of the names that we have inside of here come from the DLLs. So the specification of the DLL gives the function both a name, and then you can see this column here called ordinal. And so there are two different ways to resolve the name. If you know the exact name of it, you can use that. So you can use the name heap alloc, and it will go ahead and look up via the name heap alloc, just as an example. Or it could say, give me function 47, and that will, give me function 47 will actually go a lot faster than heap alloc. But so symbols are something that people who are creating the binary typically will use, and like when you're debugging, you want to have these symbols or names associated with things. But when you're actually running the binary, there's no reason for it to have those mappings of what the names are. And so those are actually not put in. And so actually, it used to be that symbols were sort of baked in into the binary, and they can still be, I know, in Linux. And then there's a method called stripping, which means you basically take out all the symbols. So if you were going to give this binary to your customers, you probably don't want them to have all the symbols, because then they could maybe reverse engineer your code, and then why do they need you, right? They have your code. And so there are two different places that we talk about symbols. But yeah, all of these names come from the interface that says, okay, here's a DLL, here are all the functions that it exports, and it gives actually names to all of those functions, and there's some other information about them. Okay, and some of this is going to be a little bit of review, but again, so when a disassembler is looking for a function, it typically looks for a push EBP, move EBP, ESP, write, subtract, ESP sum, and number of bytes. Now, as we saw with the Godbolt compiler, right, there are actually other things that actually can get put into the Prolog that are a little bit different, but this is your typical, okay, I know that I'm using an EBP-based stack, and so that's going to be the Prolog that I'm going to see when I'm entering a function. And then this is, again, our typical epilogue to the function, right, with the end of it being a return. And this, right, could be a leave instruction as well. we'll have to look. I can't remember on this one. Yeah, it does your typical exit, and then yeah, our entrance is going to be, well, it looks like standard in this binary, in this function. So that's stuff that a disassembler is going to look for. And, you know, there are ways to basically fool the disassembler into thinking, hey, there's not a function here because it doesn't have a push EBP function call, right? That's like the simplest one is maybe you move EBP into a different register and then push that onto the stack. So all of a sudden that signature becomes a little bit different, right? And signatures are typically a little bit fragile. We've talked about parameters, right? So parameters are going to get pushed onto the stack before it. And so that's one of the keys of understanding things like function calls, right? I see these two pushes, so I know that that is going to be the two parameters to this function, right? Which it has labeled _scanf. So I can understand that these are the two parameters for my scanf. Now we can, and we will see this when we start doing some ARM stuff with the fact that it's going to use registers for calling functions and using them for parameters. We saw that a little bit in the ARM, how if you wanted to call a particular function, you had to move one value into R0 and then another value into R1 and maybe another value into R2. So that's another way that we can do it. And it's a lot faster because, again, we're not having to use the stack, which is an order of magnitude or 10 times slower than using registers, at least 10 times. It might be 2 orders of magnitude, depending on the processor. And then here, and fast call is that method by which we can not use the stack for every single parameter, and Microsoft defines theirs, and you can basically pass arguments in ECX and EDX by default, and then all the rest of the arguments are passed from left to right in that. So if you only have 2 parameters, then it can just use those. On 64-bit, right, we actually get 4 registers to use because we have more registers with 64-bit. We also get some floating point. So this is the, I don't know if you guys remember the XMM or MMX that they used to talk about, right? So we have these registers for floating point. So we get some 4 floating point arguments that we can use. And then they have this shadow space. So again, you're going to end up seeing that when you start looking at some of the binaries of, okay, there's 32 bytes of shadow space that are going to be allocated before calling certain functions, right? And that's basically that the compiler, the function can then actually use that space as temporary storage so it doesn't have to do additional modifications. So again, these are things that you will see if you start going through some of the binaries. And again, we did talk about CDECL before, and I think I went through that and standard call. So those you just have to understand what architecture you're running on, and then you'll understand which calling format that they actually use for that. So again, standard call is going to be Windows, whereas CDECL is going to be used for a lot of Linux calls. Those are a little bit different. And then again, in class, we'll get into this more later. And so C++, right, is the sort of logical extension of C that did very poorly, in my opinion. And it tried to add these things called objects because they got jealous the fact that Java had objects, so they decided to implement themselves. And so what we end up seeing is they use the ECX register for the this pointer. And the this pointer basically points to, I talked about structures, it points to the structure that holds the information about basically where functions are located, right? So we bind sort of functions to data when we talk about objects. So it points to functions, and it also points to the actual location of the data within that object. And we're going to go and do some more examples of C++ going forward. And then understanding the different sizes of different variables are going to help you to understand what a variable is, or if it's a variable. So we have characters which are, your ASCII characters. We have unsigned characters, and those all use 1 byte or 8 bits. There is a type inside of C that talks about a word, right? And so that's going to be 2 bytes. And then all the rest of these are going to be at least 4 bytes. So typical integers are going to be 4 bytes, or a D word, as the disassemblers will call it, or a float will be a D word, and a double will be a Q word, or 8 bytes. Also a long, so long is twice as big, right? This holds integers. These hold floating point numbers. And then we can have pointers. And so if you have a pointer to a character, or a pointer to a double, or a pointer to a structure, those are all going to be a certain number of bytes based on what OS you're running. Right? So if you're running a 32-bit OS, it's going to be 4 bytes for every single pointer, no matter what. 64-bit OS, we're going to use 8 bytes. And right, this is the reason why you have to have support for a 32-bit or a 64-bit operating system, because that determines how big the pointers are going to be. So on 64-bit, we use 8 bytes to store a pointer, which is, umpteen exabytes. Or on a 32-bit, right, we're using 32 bits or 4 bytes to store pointers, which means we can access 4 gigs of possible addressable space. And so that's why, if you guys remember, right, you could get Windows XP and it could only have 4 gigs of RAM because it was 32-bit, and so there was no way to address more memory than that. All right. So I think we're, about on time. So I think I'll just do this and finish it if there's any questions. So one of the things with Microsoft, so you're going to see that they use these terms, and these have very specific meanings within Microsoft. So when we talk about a D word, right, that's going to be a unsigned, or we don't have a signed 32-bit value. Originally, Word and D word talked about the size that a machine could handle data. And so Word was the biggest size that it could natively hold. And so technically, right, if you go by the old specification, a 32-bit value on a 32-bit computer should be called a word, but it's not. It's called a D word because of backwards compatibility. And so then you have things like D word 32 and D word 64 if you are going to compile on some of these higher ones. And again, we'll see, there'll be a couple other things, like, for example, you'll see offset, right? So offset is a Microsoft MASM type of defining characteristic. And when we get into some more code, we'll see things that are going to talk about words or D words in reference. And so I'll have some examples that go with that. So does anybody have any questions on today? Comments? The audience is silent.
Everybody doing okay? I mean, no people being lost here?
What do you use to keep note during a RE? So typically, I mean, when I'm reverse engineering something, I typically put most of my notes and comments within the actual binary, or I just use a text pad. I've never used Cherry Tree, so I guess I'll have to check that out. I know some people are very like taking lots of notes. I'm lazy and I just use WordPad for all of mine, so I guess I'm old.
Yeah, it's fairly, I mean, I could definitely see using Cherry Tree or something if you had to write reports. It allows you to output into HTML fairly easily, or put it in some kind of standardized format. But so you said you do all of your commenting inside the binary itself. Doesn't that change the binary for purposes of like evidentiary gathering?
So when I'm talking about putting it in the binary, I'm meaning the database that is stored about the binary. So in your typical reverse engineering situation, with IDA, right, it basically loads the binary once, and then all of the data that you're writing back to the database is a separate file. It's I think you could kind of see it inside of my directory. It's called an IDB, or IDA database. And so every time that I write a comment, it's going to the database instead of to the actual binary. So it actually loads the binary once. Now, Binary Ninja does have the ability to write data back to the either the original binary or back to the database. And there are some benefits of that, and we're going to talk about, hopefully next time, we'll talk about. So I'm going to have you guys write a program that does some encryption. So we'll talk about it. It'll just use a very simple XOR, but we'll learn how to basically start by writing the program, and then you guys will look at the disassembly, and then I'll have another program where I did it a little bit different. And then your goal is to figure out how it works. And it's not super complicated, but it is more complicated than the original. So yeah, when I'm doing that, Brian, I'm not writing back to the original binary.
Right. Okay. So that IDB file, is that a binary? Is that easily, can you open that, or is it just going to show you gibberish?
You can open it in IDA. Like, I would not recommend trying to there. So I think the design of it is a little bit flawed in the sense that it was very closed, and it was a good extension for them at the time. But if you look at current techniques, it's not a very easily accessible binary file format. So,
Right.
people will use other formats. Like if you want to get, like IDA has the ability to save out a dead listing of the, all the assembly that you're looking in a plain text file. So you can do that if you're wanting to get it, or copy paste works for the most part.
Right. Okay.
So given a relatively simple binary, what would you lose if you were to use a debugger like Immunity versus a disassembler? So this is probably a good point to make. So there's a difference between doing static analysis and doing dynamic analysis. So if you're running a program inside of a bugger, you're doing dynamic analysis. And so one of the things that you hope is that when you actually load it in the debugger, you don't cause it to, there are two things that can happen. One is that it can behave differently if it's actually detecting that it's in a debugger, right? So there are ways of detecting if a debugger is present, right? And if it's present, right, you can basically act different if you would like. Also, so if you were to start running it on a debugger, right, you're starting to run code, and then if that code does something bad, then that bad thing happens to your computer. So one time for a class, I made a program and I said, do not run this in a debugger. And I basically had sort of a backdoor. If you ran it in a debugger, it would just do rm minus rf star on all the files that were in the directory. And I told them, do not run this, right? And I think I had one or two that actually ran it, right? And it deleted all the files in that directory because I told them not to do it, and they did it anyway. So that's probably one of the lessons that you'll learn, is that there are a couple of different, like that one is detecting it in debugger. The second one is detecting if you're in a VM. And those are things that malicious binaries will do, so that way they can behave differently, so that it makes your job analyzing them harder. And so static analysis is basically trying to understand what the code should do without actually running it. And then you can use dynamic analysis, where you're actually running it, and it goes and does the thing that it's supposed to do, and you see how it works. Yeah, I did put it, I think, in all caps too. I said, don't run it. But, that's how it goes.
Some people got to learn. Some people got to learn the hard way.
Or other ones looked in it and they saw the string that it said rm space minus rf. And they said, oh, I see what you did there. And I'm like, yeah, well, that was the goal, to make sure people didn't just run it. Yeah.
Right. All right. Well, does anybody else have any other questions in chat, or feel free to unmute yourself and ask a question. That's always possible too.
Could you recommend some patterns to look for insecure code in a compiled program? I mean, how to locate common insecure functions, hard-coded strings for passwords, etc.
Sounds like Alejandro's trying to do some bug hunting.
Well, so I mean, some of the things that we have functions that are known to be dangerous, right? So, for example, store copy is considered dangerous, right? So you can actually look in there and find every location where store copy is called, and then you can basically work your way back and figure out, okay, what function is looking for that. Or you're asking about hard-coded strings for passwords, right? So if you run right from the command line, you can run in Linux, you can run the strings program. In IDA and in Binary Ninja, they do have, or you can turn on the strings window, so you can look and see, okay, are there strings that we can look for as passwords, right? Or maybe there's a token that has a certain file format. So you can go through the binary and you can look for those pieces. And that's one of the, I've kind of ragged on Binary Ninja right now because, their Windows support isn't great, but I think their plugin architecture is it's not superior quite yet, but it's on its way to being a lot better than the support that we have inside of IDA at a fraction of the price. And so I think there are a lot of people that are using the analysis that Binary Ninja provides so that they can automatically look for those things that you want to say, this is a bad part of a program, and so we're going to go ahead and automatically find that. So I think that's one of the things that you have to look for and decide what patterns are bad, but you can go through and look for those inside the disassembly and figure out what those are.
Awesome. All right. Well, I think if anybody in class has any other questions, you can always take it up to the Slack channel. I'm gonna go ahead and ask Professor Miller where people can get a hold of him outside of the video or outside of the Slack. If they would have questions, if they're watching this video in the future, how would they get a hold of him if they wanted to ask questions?
So my email is millermj@unk.edu, and I'm on Twitter at Millhouse30, and I'm in the Slack for Breaking Down Security.
Very cool. All right. So that was the end of this session. If you found value in this, please feel free to hit up our Patreon, which I will have in a link at the end of this video as a tip jar if you're watching this after we've ended the class. You can also follow BreakSec podcast at BreakSec on Twitter, BRAKESEC. And yeah, that was it. Everyone have a great week. We'll be back for another session next Monday at this time. So hope everyone has a good night.